Hi there. Most people using coding agents today follow the same loop. They ask the agent to write the code fails, then they read the error logs, copy the stack trace, paste it back to the agent, and ask it to fix the issue. So even though the agent is writing the code, the human is still doing the debug. But it does not scale if you want the agents to work more autonomously. Because if an agent cannot understand why its own code failed, it cannot truly improve the system by itself. So in this video, I want to show a different approach. Instead of the human reading the logs and prompting the agent again and again, we are going to give the agent access to its own telemetry. We're essentially going to build a self-healing AI agent loop using Monocle, Okahu MCP, and OpenCode. By the end of this video, you'll see how a coding agent can debug a buggy text-to-SQL application without a human reading the logs. In this demo, we have a small text-to-SQL application. That SQL is then executed against a local SQLite database. The database has two tables, users and orders. The application starts in a buggy state. There are three intentional bugs that we have created in the code. The first bug is that the app uses the wrong OpenAI API method. The second bug is that the app reads the response incorrectly from OpenAI. The third one is a schema mismatch. The prompt tells the model that the database has tables like customers and products, but the actual database contains users and orders. So even if the model generates SQL correctly based on the prompt, the database query still fails because those tables do not exist yet. So we do have a realistic debugging situation. The application fails for multiple reasons. And instead of manually reading the terminal logs, we want the coding agent to find these issues by querying the telemetry. So the full self-healing loop looks something like this. We run the tests, the tests fail. Monocle helps us to capture the traces. Okahu stores these particular traces. Then the agent queries the Okahu MCP server to find the relevant traces. Then the agent identifies the root cause with the help of the trace data. The agent fixes the code, then runs the test again and repeats until all of the tests pass. This is the core idea of the video. We are not just asking an agent to guess the fix. We are forcing the agent to debug using traces. So the rule is no trace, no fix. If the agent cannot find the telemetry evidence, it should just stop. It should not hallucinate a solution. Now let's talk about the key infrastructure behind this loop. Monocle gives us automatic instrumentation. With just one line, it captures LLM calls, inputs, outputs, errors, latency, and execution spans from the app. So when the text-to-SQL app fails, this failure becomes structured trace data. And then Okahu stores these traces. And Okahu MCP makes them available to the agent as a tool. So instead of the human opening a dashboard, the agent can ask what failed in the latest trace. So this is what makes the loop self-healing. Monocle captures the failure, Okahu exposes it, the agent reads it, and fixes the code. First, we have setup_db.py. This creates a local SQLite database with our two tables. This file is important because it gives us the ground truth schema. Next, we have analyst.py. This is where the main application logic lies. It contains the text-to-SQL logic, but this file intentionally starts with bugs, and the agent's job is to fix this particular file. Finally, then we have test_analyst.py. So this file runs the test suite, and inside this file we have two different types of tests. First, we have the normal database tests, and these tests directly check whether the users and orders table exist and return some data. So if these pass, we know that the database itself is fine. And the second type is the more important one, which are the Monocle test cases. For example, we define natural language inputs like show all users and expected SQL-like outputs like select star from users. But instead of only checking the final string, we wrap these particular test cases with the Monocle validator.monocle_test case and then run the workflow through Monocle validator.test_workflow. This means Monocle is validating both things. Did the output match the expected SQL pattern, and did the correct inference workflow happen underneath? So if the OpenAI call is wrong, if the inference span is missing, or the model generates SQL for the wrong schema, the test can expose that through the traces. We also have an end-to-end Monocle test. So that one wraps the full text-to-SQL pipeline from the user question to the LLM generated SQL to the database execution. And this is why the Monocle test matter. They don't just tell that something failed. They create the trace evidence the agent needs to understand why it basically failed. And probably to the most important part of the application, which is the analyst v3.markdown. So this is the most important file for the self-healing behavior in our open code agent config. This is where we define the rules for the agent. So the agent is not just told fix the code. It is given specific debugging protocol. The rules are specifically like run the test first, wait for a few seconds for the trace ingestion, query Okahu MCP for traces, fix only based on trace evidence, archive the current version before making the changes, record the trace ID used for every fix, and repeat this particular process until the entire test pass. And that is the workflow that it will follow as described for this particular issue. So this is a prompt that we provide to our open code agent and we run it. So let's break down what's going to happen. The agent waits for the trace ingestion. So then the agent calls the Okahu MCP and retrieves the latest traces for the workflow. The first trace, you can see that it can clearly see that there is an invalid API key. So it'll make the relevant changes in the code base by using all that knowledge it gained about that particular issue through the MCP tool call through which it received the trace information, and now it will make the changes appropriately and archive the previous version. And once it basically gets and fixes that particular issue, then it will rerun the test to see which ones are the tests which are still failing. So right now it's using that information and crafting together the fix that it will make, and this will continue for the subsequent tests that are failing, where it will fetch again the latest trace information and then it will go ahead and fix it. So this entire process will continue and we'll see how it unfolds. So here you can see that it is making the actual fix with the model, and now it's rerunning the test to confirm whether those pass or not. So it's running the PyTest and it will look at each and every test case, the ones for which it has made the fix, to see if those particular changes have been fixed or not. If not, then it will continue to find the ones which have passed and the ones that still fail. So it will continuously then wait for another 5 seconds to fetch the latest Okahu traces to see which ones are failing. And then it will fetch the latest ones and then it will make the relevant changes again. So again, it starts to pick up the latest traces and it'll use that information to make the relevant changes in the code. So now we can see that it has started to identify that there are issues related to the schema with the latest trace. So those changes are also now being applied, and it will now run the tests again to check for final confirmation if these particular changes being made by the code have affected in just actually passing. And if not, again, it will go through another iteration or another loop. So here you can see that it now starts to see that a lot of them have passed, but then there's still that one end-to-end which will fail. So it will again go through the latest traces data to isolate that final bug and then make the relevant change so that that particular bug also gets resolved. And here we should be able to see the specific issue with the latest bug that comes in. And you can find here that it gets, because it uses the validator, and you can see that it's a type level. So it's running a non-string. So it will again make a specific change, but only return the SQL string. Now it will rerun our test suite. So now you can see that all of them have passed. We'll create an entire summary of all of the changes that were done with the specific changes. So here you'll see all of the different trace evidence and how it basically fixed those particular bugs by using the Okahu traces. And these are the different traces that we use for the final run, but it gives you an entire summary of what particular changes or what particular fixes were made using which particular trace evidence and what was the exact fix. And this is very important because now the human is not manually debugging. The human is just auditing the debugging process. You can take any trace ID from the summary, go back to Okahu and verify why the agent made that particular change. So the role of the human basically changes. The human is no longer the person reading every stack trace and deciding every fix. The human becomes the reviewer of an evidence-based debugging loop. And that is the real shift.